Hello and welcome to IoT Builders, a live stream where we discuss a range of topics on the Internet of Things, from embedded devices to cloud services, all from an IoT Builder perspective. It is July 5th, and this is episode 35 of our live stream. My name is Alina, and I'm a senior developer advocate for IoT at AWS. And in the episode today, we are going to cover really exciting topics around AWS IoT Fleetwise. And joining me today to discuss all these topics is Anis, who is a principal software engineer at AWS in the AWS automotive team. Hi, Anis, how are you?
Hello, Alina. Thanks for having me. I'm good. I hope you are also doing well.
Yes, I'm doing well. Thank you very much. We are really happy to have you. So thank you very much for agreeing to be with us today in our IoT Builders episode. So Anis, tell us a little bit about yourself. What do you do?
Thanks for having me today. My name is Anis. I'm based in Berlin, Germany. I joined Amazon 4 years ago, and I'm currently a principal software engineer in the AWS IoT Automotive organization. Yeah, probably one personal thing. I have 2 kids, married, and enjoying life and enjoying IoT.
Very nice. Yeah, so we're both in Berlin actually. So this is really nice. It's automotive is actually a really interesting topic, and it's gaining more and more traction, I think. So I would like to ask you, what do customers approach you with when it comes to problems and challenges in the automotive space? So what are customers saying?
Right, Alina. So my personal perspective is that the automotive industry is going through a very massive transformation, specifically with the massive growth of data and data-driven architectures in the automotive industry. OEMs and other industry players are recognizing that with the scale of their vehicle fleets and electrification autonomy, they are seeing that a massive amount of data is going to be needed to continue building somewhat a closed loop based on data to continuously improve either vehicle software or vehicle safety. And the challenge with data governance, data management, data processing is more and more prominent. And that's what we see also and what we hear from our customers so far. They're looking for at AWS as a well-established cloud provider with the infinite scale that we have. How can we help them manage this data at scale, but also look at some of the undifferentiated heavy lifts that AWS is very good at solving.
I see. Okay. So basically, what have you guys built, right? So you've built a service, right, to deal with to tackle the challenges that customers approach you with, right? And this is how IoT Fleetwise
Right.
was born.
Right. So we looked mainly at 3 main problem spaces. The first one is they are all data centric. The first one has to do with the data fragmentation. So with a lot of vehicle models and vehicle platforms available on the road, within a single automaker, you find multiple vehicles designed and architected to produce certain data set in a very specific format. And when they come back to the cloud, there is a huge challenge with the data fragmentation. So you would need to have something around unifying the data formats across vehicle models and components, making this a huge challenge for creating fleet-wide insights. So that's the first problem space we looked at. The second problem space we looked at was the data tsunami. The data tsunami has to do with the vast amounts of data from advanced sensors like camera or LiDARs, right? That makes it very difficult and expensive to isolate the data signals you need in a sea of noise. So that's the second problem space. The third problem space is the delays. So you look at data at the fleet level with all the unreliable connectivities and the complex road networks. You might look at certain data sets from very specific vehicles on the road that you absolutely need to take a data-driven decision. However, you are faced with the nature of physics. How do you make sure that this data arrives on time when needed? So these are the 3 problem spaces we looked at. And we said, let's look at the common denominators here. So we know that pretty much every industry player looks at building either in-house or purchase a connected vehicle platform. Mainly from a connected vehicle platform perspective, you do have multiple layers. So you have a vehicle domain, where you have ultimately one or more data collectors. You have another domain, which I call connectivity and transport. This is basically the glue layer between edge and cloud. So how do you connect securely an asset or in a vehicle on the road back to the AWS cloud or to the cloud? And the third layer is now the ingest at scale. So we are still in the vehicle collection phase. So collect from the vehicle, transport the data, and then ingest at scale. These three main, stack layer. These are like the three layers in the stack. Then later, once you ingest the data at scale, how do you make sure that this data is defragmented, is standardized, is unified, so that your downstream data lakes look at the data with a unique taxonomy? And this is how we have thought about looking within this stacked architecture at some of the layers that we could solve in a managed way using the AWS well-established services to create, basically make some of these steps in the stack managed, so that industry players can simply trust there is a managed service that takes care of acquiring data from vehicles at scale, transporting the data securely back to the cloud, and then ingesting at scale, then doing some of the data defragmentation and standardization already upfront. So it's pretty much most of the data management pillars will be managed by the AWS service, and the remaining parts will be very centered around the data lake, where it's an entry point for a lot of data-driven applications. So that's how we basically looked at the shared responsibility model, where AWS takes care of the undifferentiated heavy lift, which has to do with acquire, ingest, and acquire, transport, and ingest, and then standardize. These are all undifferentiated, and then look at the rest of it, publish the data to a data lake where industry players can take it from there and build data-driven applications. And this is how we came up with AWS IoT Fleetwise. This service has been launched, generally available in September 22. It was 2022, and it was previewed at reInvent 2021. So the service is around probably 8 months old now. We are very excited about the service and its success in the industry. And we, of course, like any other AWS service, we work backwards a lot with customers. So we see the more we get, customer onboarded, the more we understand that we still need to build a lot, and our let's say problem space is increasing. So we see a lot of undifferentiated heavy lift that we want to, or boring stuff that we want to do on behalf of customers.
Yeah, I see. So this is interesting. From a developer perspective, could you maybe elaborate a little bit as to how, what the developer experience with Fleetwise is? Like, does the journey start in the cloud, or does the journey start at the edge? How does it work? How do people, get started?
Great question, Alina. I think before I want to scratch the surface of how a developer journey is, I want to first emphasize on certain use cases, because I know developers appreciate always when they start solving a concrete problem. So let's take the example of a developer that wants to basically monitor, for example, an electric vehicle battery health, right? And they want to, for example, improve the range estimates. So you have an electric vehicle that has battery packs with a lot of battery cells, and they want to have a lot of data acquired from a vehicle fleet to make sure that they can monitor in near real time the electric vehicle, but also trigger certain applications downstream based on this data. For example, for improving the range estimates and reducing the range anxiety, right? Anxiety. So the developer journey starts, of course, in the cloud. So we are inverting the paradigm. So the way we think about data acquisition and data modeling is that traditionally industry players start in the vehicle. So they build a vehicle agent that basically it's heavily or deeply embedded. It looks at the sensors and actuators in the vehicle. In this case, for example, in the battery or the electric vehicle space, we are talking about the battery management system that has various networks that outputs a lot of data over multiple hybrid networks like CAN, CAN-FD, and other proprietary protocols. And then they build a collector that basically somewhat takes very frequent data points packs it in and then ingests it into a backend or logs it in a hardware. And then the data arrives at the data engineer side in the cloud, and they start then curating the data manually or build pipelines to basically start filtering the data noises, reducing 90% of it just to get to that part. With AWS IoT Fleetwise, the developer experience is inverted. So we first start with what we call the vehicle modeling step. So we have built a service called AWS IoT Fleetwise Designer. This is a set of cloud APIs that developers use to first, before even collecting a single byte from their vehicles, they describe the vehicle knowledge graph. And I think people here in the audience might have heard about this terminology before. It's a well-known construct in the industry that helps basically engineers describe an asset. So in this case, we are describing an electric powertrain. So we're saying we have a battery pack, the battery management system, we have X number of cells, and we have a battery voltage, we have a state of health, a state of charge, but we have also a lot of cell level temperatures and voltage. So all these data points, what we call sensors and actuators, these we have APIs that help engineers model the battery management system in the cloud using our designer service. Once you have that defined, we give them a set of other APIs to start defining what we call a data collection campaign. A data collection campaign is a construct that allows engineers to simply say, okay, I'm looking at a very specific scenario in my electric powertrain. So I want to look at the battery temperature when the weather information or the outside temperature is, say, 50 degrees Celsius. I hope we don't have that in Germany. And I want to collect the battery voltage every time the temperature exceeds 40 degrees or 50 degrees. You formulate that as an engineer in the cloud as a data collection campaign. So remember, we are still in the cloud. We haven't deployed anything to the vehicles. We haven't received anything downstream in the vehicles. We are still in the cloud. Then you could, as an engineer, go ahead, create simulation workloads, validate that this campaign gives you the data points you need to develop your downstream application before you even collect a single byte from the actual fleet. So all of it is done in the cloud. Once you are sure that your data collection campaign is very well tuned, that your timing constraints are considered, that all the signal data you need is already pre-configured, you can go ahead and decide, hey, let me deploy this data collection campaign to, for example, my fleet that it's on the road somewhere in Berlin. At that point, we take over. So we take over this data collection campaign. We deploy it to the fleet of vehicles. So this fleet of vehicles is already pre-provisioned with our vehicle agent. So our vehicle agent, it's an embedded software that sits inside any of the electric control units that you have in the car, whether it's the BMS or TCU or an infotainment. Where you deploy the agent must have access, of course, to the actual raw data somewhere. So that's part of what you also model in the cloud. How do you physically access from the agent specific networks like the CAN bus? And it will take care of enacting that data collection campaign and monitoring specific events that you have of interest. The moment the data snapshot on that specific vehicle has been reached, for example, in the scenario I provided, we are talking about a very specific outside temperature. What we do is that we take care of buffering all the data and we wait for that event to happen. Once that event happens, we take the snapshot, we ingest it securely back to our AWS IoT Fleetwise data services. And we make sure that now that we apply all the defragmentation steps, the standardization steps, and the enrichment steps, which I will explain later, hopefully, as we progress in the discussion.
So I think what's interesting about this is also the fact that if, for example, the connectivity is lost temporarily, this buffering of data is not happening just in memory, right? So you ensure with the edge agent that the data does eventually arrive in the cloud. And then with the cloud side of the solution, you ensure that basically eventual consistency is reached with the data, even if it's later, because the device lost temporarily connectivity, right?
Correct. So our vehicle agent, of course, is working in hybrid mode. So it continuously, of course, monitors the connection health. And then there is, of course, as you well know, in any IoT stack, you have automatic retries on multiple levels to make sure that the connection or the TCP session is kept healthy. And of course, if we lose connectivity completely, our circular buffers that we have in the agent are kept in terms of memory or RAM usage, and they get eventually flashed on a disk partition or in a shared memory just to make sure that we don't overwhelm the RAM. All of this is configurable. So customers will get to configure whether this data is compressed locally or not, which partition in the file system the data should be stored. The moment we see connectivity reestablished, we will try to ingest that data back to the cloud. So the risk of data loss is somewhat reduced with this technique. Of course, you cannot go indefinitely. In that case of collecting, indefinitely data, you need to cap it, just to make sure that the non-functional requirements are respected. So that's on a high level how we try to kind of close the loop. Of course, what we haven't discussed yet is what is that part that we do in terms of data processing or data management. That part, I think, is where I think the actual data-driven decisions will be triggered. So I have actually one slide that visualizes the engineer or the developer journey, which I want to share with you. So
yeah, sounds good. Before that, I still wanted to ask you, because we are still talking about the data ingestion, I just wanted to ask you what format is the data in? So what is it JSON that you are ingesting, or is it protobuf that you are ingesting? What is the format?
So
the encoding, sorry.
Yeah, so the vehicle to cloud data format is something that we have designed and modeled to be very resource friendly. So on the data format itself, we have our vehicle to cloud payload is defined in form of protobuf. So it's a binary encoded data snapshots. And we, of course, use a compression algorithm to make sure that the data is also compressed in transport, but also at rest in the vehicle. The specs and the data models are available as part of our vehicle agent code base, which is open source. It's available in GitHub. It's continually maintained, which developers can look into. They can look at the data models. They can, extend it if they see needs of that. We had customers actually looking at that, and they gave us a lot of good feedback on how we can optimize the schemes of the protobufs. We are, of course, continuously extending and trying to look at the latest and greatest approaches in vehicle to cloud ingest optimization, especially now looking at MQTT3. That's the main transport we use now. We have now AWS IoT Core supporting MQTT5. So from a payload perspective, we are also looking at much bigger payloads. We also are looking into ingesting into other destinations, right? In case, telemetry on MQTT is fine, but probably you might have a different snapshot for future use cases around video ingest or around, bulk data ingest. You might want to you might look into, a direct S3 ingest. So this is why we decided to make this agent more open source, so that developers have the option to extend it for the use case they need it, they see it right. So this is our view on that.
Sounds good. Yeah, so let's have a look. I think you wanted to share something with us.
Yeah, so I wanted to quickly kind of show or kind of share a slide showing the typical developer journey here, end to end, how they can interact with the service. Is my screen visible?
Yeah, we can see it.
All right, so as I was describing here, so there is, of course, developers start in the cloud. So this is the cloud domain, what you see here. And you have the vehicle engineer coming here. They are modeling basically the vehicle sensors. They model them in some design construct, which we call signal catalog. This is an inventory of all sensors and actuators. In our case, we talked about the battery management system with the underlying battery pack. Then, of course, in this modeling step, I think I briefly spoke about it. We model two things. We define the sensors and actuators, and we assign them fully qualified names. The fully qualified names are uniquely identifiable across vehicle models. That means if you have car A that has a BMS system, or it has a very specific signal in the vehicle that speaks about state of health or state of charge, and another vehicle that from a previous generation that has a different signal name, this fully qualified name is unique across the two models. So that's why we store them in a single signal catalog. We use the vehicle signal specification to make sure that signals are uniquely identifiable, and that's how what we use underneath to create this standardization layer. So I will come back to this later when we talk about data processing. The next step is, once you declare these signals, you need to attach them to physical network interfaces in the car. So for example, you are taking battery cell voltage, that specific in a specific cell in your electric powertrain is connected to a CAN bus. So that specific signal belongs to a specific CAN frame, right, in your BMS system. Mm-hmm. And so you, again, in the cloud, you take your CAN frame encoding information that you typically find in DBC files or in 5x files or AutoSAR XML files that describe exactly how your frame or how your signal is encoded inside the CAN frame. You import that in the cloud. The service will take care of creating the decoding rule for that signal and attaching it to the fully qualified name. So we are still talking in the cloud. We are still modeling the vehicle. That's in step one. Then in step two, as I talked before, the data engineer says, hey, I don't understand anything about the vehicle architecture. I only care about data. So let me go ahead and start create a data collection campaign where I only use the fully qualified names of signals. Only that. I don't care how these signals are encoded inside the vehicle. That's not of my interest. I only care about the signal names because I believe they are useful to my data-driven development. So they create the data collection campaign. In our case, they take, for example, we said we're going to collect or monitor the battery cell temperature based in comparison to the outside temperature. They model the data collection campaign. They can simulate it in the cloud, right? Make sure that they have the right tuning. And then they can apply the campaign to a fleet. So applying means that in the cloud, they go ahead, either through the console or through a command line interface, go ahead and review the campaign, approve it. And then once they approve it in step two, the campaign is deployed, right? This is the yellow button here, is deployed to the fleet of vehicles. So this is not a single vehicle. It can be thousands or millions of vehicles. Once it's deployed here, the vehicle agent, our fleet-wise vehicle agent, will eventually access the vehicle network, look and filter for exactly these signals that you have interest in, decodes them, buffers them in memory, put them in circular buffers, and then starts waiting for the conditions that you have defined in your data collection campaign. Once these campaigns are, these conditions are met, the ingest happens back. That's where the fleet-wise service takes again the control in step 4 and does basically 3 different operations. The first one is ingest. So that's, I think most of the community knows it very well, right? If you are having an MQTT broker, you have basically reserved topics, MQTT reserved topics that we internally use to ingest the vehicle traffic. This data is then routed into our data plane, into our fleet-wise data plane, where the first thing we do is that we do data validation. So we receive that vehicle data, we look at the vehicle model, so we use this model information, we check, is this vehicle now reporting what it's supposed to report, right? That's the first step. That's why we use the model for that. And then we look at validating the data integrity itself. For example, in your modeling, you have defined the temperature to be between minus 40 and maximum 40 degrees. The data point arrived at 60 degrees. You might think that this is either a data drift or this is simply an invalid value. So you could define also these rules in the model, right? So we do this range validation. Then we take the signal from the data, we give it its fully qualified name, so that in your data lake later, you only use this fully qualified name independently of the vehicle model or model year or vehicle platform variant. So this is what we call data enrichment. Then later we deliver the data, right, in multiple formats back to your storage destination, whatever storage destination you wish. For example, if you are doing real-time monitoring, you might want to look at something around time series databases. For that, we have a storage destination, which is Amazon Time Stream, based on which you could build a lot of real-time monitoring capabilities using Grafana, for example, and start visualizing the behavior of the data and how the data is evolving at the fleet level. Or if you are doing batch analytics and you simply want to go and look for anomalies more at the fleet level, more with like on a daily basis or on a monthly basis, and you want to have this data now delivered to your data lake as an S3 Parquet file, for example, then the service will take care of pushing that into your S3 bucket of choice, from which you could build your downstream data analytics pipelines using the well-known technologies like Glue and Athena and Redshift and Elasticsearch and so on, right? The key thing here is in step 5, because the heavy lift, the undifferentiated heavy lift here is that the data fragmentation doesn't exist anymore, because you are querying vehicle data using a single taxonomy, which is using a single unified signal names. So you query vehicle.powertrain.battery.cell1.temperature. You don't care how this signal is encoded in vehicle of type A or vehicle of type B. Right. So the data all looks alike. So the data standardization is applied. So your query engine becomes agnostic of the vehicle architectures. That's basically some of the key values of the data enrichment capabilities that we have now. You could run fleet-wide queries to make sure that this is, and build, of course, a lot of downstream applications there to monitor what you are looking for. Now, these campaigns, I mean, I think one of the steps is not visible here. You can always fine-tune the campaigns. You could always interrupt the campaigns. You could always suspend the campaigns and say, I want to change something, or I want to add another signal. And I prepared today a small demo so that I could share it with you later that will hopefully give it more details on this one.
I see. So generally, how much data is IoT Fleetwise storing?
So I think again, it differs from a use case to a use case, right? So if we are talking about basic telemetry data-driven applications, right? For example, you are doing fleet-wide, anomaly detection, or things like you are doing a driver behavior, observability. You are doing certain like remote diagnostics related, campaigns. These ones are in the range of telemetry, right? In the range of telemetry, we are talking about few megabytes per day per vehicle, right? So that's what you typically see in telemetry-driven applications. If you are thinking about things around, ADAS and autonomy, right? So you are talking about a much bigger data snapshots per vehicle, especially if we're talking about camera, specific driving scenes, and you're looking at, raw data eventually. That's where it can get interesting. However, the problem there is that it's sorry about that. I just got interrupted.
No problem.
Yeah. So in certain for these use cases, we are talking about a much bigger, of course, payloads, probably hundreds of megabytes per day. Now, we are still nowhere close to the traditional systems where data is being logged all the time, right? So the data logger use cases are by far more verbose than this technique, because in the data logger use case, you typically have a hardware logged into the car and it's logging everything in the vehicle, which is terabytes of data. So when you use something like, like selective data collection, like what the capability that Fleetwise provides, you are looking at probably reducing in factor of 10 or of hundreds in certain use cases, because you're looking at this very specific scenes, very specific driving scenarios. So, and this is somewhat, it's a mutable thing that you could change over time and make sure that you could align it. You can make it more verbose, less verbose, based on your downstream data needs. So this is pretty much like, it differs, as I said, from use case to use case, but anywhere from megabytes to gigabytes per day, that's the range I would see.
Yeah, and you could configure this via the campaign, right? You could also configure what types of data you're sending via the campaign, and that would also
Correct.
probably dictate how much data you're storing.
Exactly. Yes.
I see. So, I mean, right now, I think for me, the next of logical step is to try to understand a little bit more about what's happening at the edge. So, what do you think, Anis? Could you maybe tell us a little bit more about the edge agent and maybe a bit about the architecture?
Sure. Great. So let's dive deep a little bit here into the edge architecture. So um, I think I know developers love to look at the stacks and looking at threads and other stuff. So our edge capabilities are basically designed around POSIX APIs. So mostly, I mean, I think most of the embedded engineers, they come probably from, anywhere from microcontroller programming towards user space applications, depending on their, of course, field of expertise. We looked and, decided to basically look mostly at the POSIX APIs, and we designed our AWS IoT FleetWise Edge around that. As I said, we'll share offline, of course, the link to the GitHub repo where developers, of course, can take a look at the code. And we have an extensive set of developer architecture docs there in details on every layer. But on a high level, our software is a multi-threaded C++ application, a mix of C and C++ that basically tries to leverage as much as possible the POSIX APIs. Something that from a runtime perspective, I think you are looking at running it typically in anywhere from single core to quad core systems. So from a non-functional perspective, this is still a very tiny embedded application that can run anywhere from, a range of, 100 MBs RAM to 200 to 300. So it can run on any pretty much performance silicon. We have run it on 32-bit, 64-bit systems, single core, multi-core, yeah, we definitely have seen a lot of course, platform-specific adaptations that might be needed. We have seen a lot of developer contribution around that, especially in our GitHub using our pull request, and this information is available. You can, the team here, the community here can take a look. So as I said, it's a multi-threaded application. We do, of course, leverage a lot of the existing AWS SDKs that are available, especially for MQTT and accessing other AWS services. So we use the native SDKs there as much as possible. We, of course, use a lot of the Linux kernel headers to make sure that we access things like, driver information, hardware timestamps, and other stuff. Yeah, so that's on a high level our kind of edge, on a high level our edge specifications. And as I said, in our GitHub documentation, there is an extensive developer architecture doc that explains exactly each of the layers we have in the software and what each layer is doing. Of course, I mean, of course, the system can be decomposed. You could move things right and left. You could even rewrite it in a different language if you want. If your SoC or your silicon doesn't really, or your board support package doesn't support a specific language runtime, we had customers that rewrote using our specs and our design the same software in a different language runtime. So again, that's the benefit of open source, and I think this is giving developers flexibility is definitely something extremely appreciated. I like it myself as a developer.
Yeah, I put a link in our comments here with Edge Agent Dev Guide. I assume that this is the one you are referring to, and there's a part there about the software layers, which looks very interesting.
Yes.
So yeah, have a look at that.
And by the way, we do have here just a call out here for the colleagues. I think we do have a lot of tutorials on how to install that on, for example, Raspberry Pis, $10, $10 sort of, small devices, on some other reference automotive grade boards. So it's all available in the GitHub documentation. the team here can take a look at that, and we are very happy to take any inputs or pull requests based on their findings.
Mm-hmm. Sounds good. So maybe, I don't know, I know you touched upon this, but maybe could you tell us a little bit more about how the Edge agent can be extended by developers? Like how easy is it?
So we can, of course, go into a little bit more details here on the Edge side. So we do have a couple of design patterns that are baked into our Edge architecture. For example, let's take the scenario of, for example, supporting or adding CAN-FD, for example, as a new network interface that our Edge agent would like to consume data from. So the design pattern that we have built in the agent is that we follow a dependency inversion design pattern. So we have somewhat an abstract interface that you as an external connector, you could build a connector, just implement that abstract interface, which we call here the vehicle data source, what you see in purple here, and just implement it. You could decide to run it in the same process or in a separate process and have your own IPC in between. And then you simply would feed the data structure that the Fleetwise agent expects. This is part of the interface itself. And then simply the rest of the system will simply work if you obey to that contract. So that's one possible extension we have seen already. Some customers have tried. We also have seen other extensions. For example, some of the customers said, hey, we don't have the data on the CAN bus. We have it in a, for example, it's available over a TTY session, or it's available over a UART SPI link, and we don't have it on CAN. So what can we do? We also we created an example in our code base that shows how developers can plug their own data sources to our vehicle agent without activating any access to the CAN bus. For example, GPS coordinates. If you are running on a TCU, GPS coordinates might be coming from a GNSS module on that TCU. It's not on the CAN bus. How could you take that? Or, for example, Wi-Fi signal, or there's plenty of data points and vehicle properties that are not on typical vehicle networks. And for that, we also gave an example how you could plug it easily into the Fleetwise agent. So we had also other extensions. We had also customers that said, hey, how can I run this now as part of a container? Because I'm managing all the applications on my vehicle using a container orchestration. Again, we also delivered as part of our GitHub a container image that's available. The colleagues here, developers, can take it from there, and then they can add their own dependencies. We provided also Yocto Linux manifest that or a recipe that developers can add and include in the AWS. There is the AWS Meta, of course, recipe that's available. So we have done a lot of efforts around enabling developers to get their agent to run on any sort of build system. And also we gave some examples around, how do you plug the agent to non-standard vehicle network interfaces like CAN or anything, or Ethernet, right? So these are all part of the vehicle agent. They are templated, they are examples. We also provide, as part of our Edge agent, a lot of simulation tools. So if you look in the code base later on, you will find the directory called tools, and you will find, for example, a CAN bus simulator already baked in the code base that you could use to simply run the agent on a virtual machine somewhere, and then simulate the CAN bus traffic that you need. And you could use that to validate a data collection campaign without actually going to, to a specific vehicle or going to have a hardware. You could do all of that in a virtual machine somewhere in AWS Cloud using an EC2 machine. At best, you could take something with a Graviton processor, that's an ARM processor, ARM v8 processor, and you will get it just seamlessly compiled. On that, you could run the simulator and then start having a virtual vehicle in the cloud and start validating your data collection campaigns. So all of these things we try to, as much as possible, deliver as part of our GitHub as examples to developers to encourage them to try out the service and try out the agent.
That sounds really great. So I pasted a couple of more links, including the link to Meta AWS. So in the AWS for embedded Linux, Meta AWS, you are going to also see the recipe for Fleetwise. So have a look at that if you're interested, and if you're interested in building Yocto images. So I mean, I know, Anis, that you wanted to actually walk us through a real use case. And I think right now it's the right time for us to have a look at the use case that you wanted to show us.
Great. So let me take. I mean, I know that we all like visuals. So here I took I mean, again, I'm back to my. I like electric vehicles, and I believe they will have a great future. So that's why I tried today to give you an example around that. So let's imagine we have a fleet of electric vehicles that's on the road, and we are trying to basically look at, in a fleet of 1,000 vehicles, what could go wrong from an electric powertrain perspective. So we created a first campaign using AWS IoT Fleetwise that is looking mostly at, is there any diagnostic trouble code set? What is the current state of health? What is the min and max module temperature? What is the min and max module voltage? So we go ahead, we create the first campaign and deploy that to the fleet of 1,000 vehicles. Okay, so that's the first campaign. I take back the data, I visualize it using Grafana, and I start looking. After an hour, I do see that there is 979 vehicles which are on the green path. The decision of green or non-green, this is something that you could set as a threshold on your side and say, hey, all the values, there is no DTCs, the state of health is fine, the temperature is within the ranges, the voltage is within the ranges, everything is green. However, I found out that 3 vehicles have faced some challenges. So some of them might have some diagnostic problems, some trouble codes, some others might have, unexpected temperatures and so on. So for that, the next step is I want to zoom in now. So I create a new cohort. So I create a second fleet that is only targeting these 3 unhealthy vehicles. So you see already that I'm zooming in. Now I forget about my 1,000 fleet. I just focus on these 3 vehicles. I create a second campaign where I start sampling the data more frequently. So probably in the campaign 1, I'm collecting data every 10 seconds. On the second use case, I'm just looking at it more frequently. So I want to collect more data from exactly these 3 vehicles. So here, I'm going to increase my data footprint, but I will do it mostly vertically, not horizontally. So the fleet is still using the campaign 1, the bigger fleet. The smaller fleet, I will increase my sampling rate to start seeing more data. And here I did 2 things in the second campaign. So I took the original campaign and then I duplicated it and I created a high frequency sampling data rate, right? And then I added more signals because I want to know more. I want to know, for example, the outdoor and indoor temperature. I want to know the current speed, the odometer information, the tire pressure, and so on. I go ahead and they deploy the second campaign to the 3 new vehicles, the 3 vehicles that I'm suspecting they are not healthy. Again, I visualize, and now I have more data to visualize, right? I have now, for example, the air conditioning, outside temperature is there. I have a better zoom in at more data points from these vehicles. Now, I might have concluded here, based on this analysis, either visually, right, or using some, data-driven decision that I got out of my pipeline on these 3 vehicles, that probably there is a bug on the electric powertrain here. And that's where I will probably, either in a simulated fleet or in a real fleet if I have a test vehicle. But here, I think in this example, I just said, hey, let me create with the same ECU software a simulated vehicle. And I create a third campaign that basically compares with the same recording of data that I collected from the previous vehicle. So I have the same driving scene. I simulate it back in the cloud. And I create 3 more vehicles in the cloud, no real vehicles. I put them in the same conditions, but with a new ECU software. And then I deploy my third campaign, right? And with that, I could do easily A/B testing without really touching anything on the real fleet. So this is like the scenario or the use case where you could use the campaign management dimension of the AWS IoT Fleetwise service to do 2 things. Do the first thing, which is pure fleet observability. So you are doing typical anomaly or like remote monitoring use cases. And the moment you see some anomalies, that's where you could start saying, hey, let me do some A/B testing. Let me zoom in into the real data. So I do a snapshot or a zoom in into the unhealthy vehicles. And then later, if I have a CI/CD pipeline that looks at continuously on a daily basis, publishes a new ECU software, I will have my simulated fleet in the cloud, put it under the same conditions, and then create a third campaign, target the simulated fleet, and see whether the same pattern is happening, right? I know that in embedded systems and in automotive in general, you cannot meet the same timing constraints. And I think vehicle engineers, they know this very well, that you cannot simply get the same timing constraints in the cloud as in the edge. So a simulation in the cloud might not give you exactly the same timing at the microsecond level. But at least if you want to do a sanity check, you want to make sure that, hey, in 99% of the cases, I'm not going to see the same problem. You get already some kind of, good feedback already in the cloud without any physical deployment on the car. So these are like some of the undifferentiated heavy lifts that we thought, industry players could benefit from. And that's basically the demo I wanted to share today. It's unfortunately not a live demo, so I think due to time and so on, probably we cannot do a live demo today. But yeah, I tried to take some of the snapshots here and try to explain it to the community here.
Yeah, I think it makes a lot of sense. So, and I particularly like the the theory behind A/B testing and the fact that you can actually do A/B testing easily with Fleetwise. I think this is an amazing feature, and it's also a feature that it's a lot of heavy lifting that Fleetwise actually does behind the scenes to enable developers to do this, because actually building this from scratch is far from trivial. So probably some of the developers who have joined us today might have done it, but it's actually far from trivial.
Right.
So thank
And
you
I
very
think
much,
that,
Anis, for sharing
yeah.
that.
Right. So yeah, I mean, I would encourage everyone here to take a look at that, especially the capability of running, pretty much a simulated vehicle with simulated vehicle data in the cloud, targeting them with campaigns, and look at data drifts and data variations while you are still in the cloud without any physical interaction with the car. This is very powerful, right? And I think you can derive a lot of data-driven decisions purely in the cloud, right? You don't need to have a physical car to validate certain of your assumptions. So this is very powerful, because one thing is collecting data. Second thing is how do you use this data efficiently? If you have recorded data, as I said here in campaign 2, from the real fleet, you don't want to say, hey, I collected this data, it's available somewhere, but now I need to go ahead and do an over-the-air update to a specific software on specific vehicles and go ahead and record. You would rather say, let me use that data to put my simulated vehicles under the same conditions and then verify my new software or my new configuration in the cloud already before really triggering a test drive. So like, this is mostly probably not a production use case. I'm here more talking about like the vehicle development lifecycle. You're still not in SOP yet. You are not in production yet, but it's very powerful in terms of A/B testing. And I think a lot of money is spent around that. So having capabilities to spin up an EC2 machine in the cloud, put a simulated workload, have an agent that does collect what you want, simulate the data based on existing, real world data, and deploy a campaign with a click of buttons. I think this is very powerful.
Yeah, and especially because it speeds up the developer experience as well. Because generally in teams you have different specialists, right? So somebody's working at the edge, somebody's working in the cloud, somebody's working with data. So you've got data engineers, data scientists. So you don't really want to make them depend on waiting for some processes being ready at the edge and waiting for edge deployments and so on, and waiting for the hardware to arrive and be ready and so on. So I think this is really cool and really powerful. So I mean, there is so much actually. So the more we've been talking actually in this episode, the more I realize that there are so many more questions that I want to actually ask you. We still have some time. Perhaps something very interesting for me would be if you could go a little bit more into details around around vehicle modeling. So how is it modeled? How do these graphs look like? I would be really interested in seeing that.
Right. So I also had a simplified slide here that basically gives the community here a view on how we perceive or how we think about the vehicle model. So now you could think about the vehicle model, as I mentioned earlier, as a knowledge graph, right? We today call it signal catalog, but if for people that know what a vehicle knowledge graph or a knowledge graph is, they would see it more as a design construct that basically defines how entities are interconnected, right? So as an example here, just to apply to the vehicle, think of it as a tree. So you have a vehicle, the vehicle has multiple domains, right? It has multiple attributes. For example, the vehicle identification, you have a chassis, you have a drivetrain, probably have a body controller. And each subdomain has other, sensors in it and actuators, right? So how do you get to design this dependency between the asset that you are modeling, which is the vehicle, and then its underlying entities, which are sensors and actuators? And most importantly is that how do you create this hierarchical, uniquely identifiable taxonomy, pretty much, to query anything from this tree, right, uniquely? So I took an example here. So if you say, hey, I want to know where speed is and how to identify speed, you would declare it in the knowledge graph as speed is part of the transmission ECU. The transmission belongs to the drivetrain domain. And then you would create a unique qualified name for the speed called vehicle.drivetrain.transmission.speed. You would declare that as a sensor. You could give it a data type, right? It's 2 bytes here. You could give it a unit. You could give it a min and max. And then you could give it a description. So with that, if you scale that among all the sensors that you have in the vehicle, you could ultimately have a knowledge graph that can tell you anything about your vehicle in the cloud already. So you could query the vehicle model and say, hey, can you give me all the nodes in my graph that are basically having speed? So speed might be in the engine domain. It can be also in the transmission domain. You might get 2 nodes back. One is vehicle.ecm or engine control module.speed. The other one is drivetrain.transmission.speed. They're both entities. They might be physically the same, but they are modeled in the graph as 2 nodes. So later on, when you kind of scale this concept a little bit to relationship between entities, right? So you could say, for example, in my chassis, I have, an axle, and this axle has 2 rows, and each row has 2 wheels, and every wheel has a tire, and every tire has a pressure, right? So you have basically a relationship between a sensor and an actuator, right? You have a concept of a branch. So you could query, for example, say, hey, I want to get all the data from vehicle.chassis. Think about it. It's very powerful. So you could say in my data collection campaign, I don't want to collect vehicle.chassis.axle.row1.wheel.tire.pressure. I would rather say, hey, collect me everything from vehicle.chassis. Then automatically, all the underlying nodes will be collected for you. That's what the knowledge graph or the vehicle model is useful for. The second dimension here is the modeling, is the validation part. Remember in the example I provided here with the speed, you have basically a unit. You have also min and max. Think of this that you have a service that takes care of validating value ranges automatically for you as you are ingesting data, right? So that's also something that helps you reduce noise a lot, right? You don't need the noisy data unless it's unexpected, of course, right? We are not talking about the unexpected, probably test-driven data points. I'm talking more about general purpose, data ingest where you want to get rid of the noisy data, the data that's probably corrupt, or the data that's basically coming from a faulty vehicle, or a data that's coming from, an unexpected scenario. So you have all these things that we apply for you. So we give you one capability here. How do you model your vehicle? Create a knowledge graph to know everything about your vehicle properties. That's one part. The other part is that how do you use the power of this model in your ingest pipeline? So when the data is ingested, we use the model to unify your data, make it all look alike using fully qualified names, and applying the necessary validation upfront for you. On top of it, we use it to give it the format, the data in a format that's suitable to your data lake, right? Whether it's a Parquet file with a very specific structure so that you could ingest it through Glue, or a schema on read, just ingest it in your Athena database, start querying using fully qualified names that you take from the model. So your model becomes the core of your data-driven architecture. You could take this knowledge graph, make it at the core of your schema catalog, and then all your applications are built around this model or this knowledge graph. All your applications speak the same language, the same taxonomy. That's our ultimate goal, right? Centering the vehicle data architecture around a knowledge graph. And you could think now, just as a think big here, that you could expand this concept beyond, giving, or organizing sensors and actuators. You could think about anything that's dynamic. Give it a dynamic dimension here. Think about vehicle shadows. Think about, calibration information. Think about anything that can be modeled as part of the knowledge graph. This is a very powerful entity in every data-driven architecture, in my view. And I think it's becoming very prominent in the digital twin world. So anyone that works either in the industrial or in the automotive space, they know this concept of digital twin, where you need an entity like a knowledge graph. So that's on a high level what I believe. I think we can spend hours on this one. I like this topic, but just I hope this was useful. Just on a high level, the vehicle model concept.
Yeah, absolutely. Definitely very interesting and very useful. And if anyone has any questions about this, feel free to drop them in the comment section. And Anis is going to respond to you if there is time, still by the end of the episode. But if not, we will also do this offline, and you'll get your answers. Yeah, so this has been really, really insightful, Anis. Thank you so much. I would like to ask you a bit more about how developers can get started and where some information is and what is your call to action. But before we get there, any last words that you would like to share?
I really enjoyed the session today and the questions, and I really kind of, I personally, we think in AWS that there is no success without developer inputs, because the whole platform is built for builders. So our first customer is the builder. So these sessions are very, very, very important for us to get some, feedback from the builders. And as I said, the more we build in the open source space, the more you get useful feedback. So I encourage everyone here to just take a look at all our documentation, at our GitHub page, look at our code, at our design, give us inputs, try it out, give us inputs, give us pull requests, give us feedback in general. As I said, it doesn't cost anyone anything to go ahead and take out the code, run it in their own virtual machine, either locally or in the cloud, run the simulation, try out the service, and feedback here. The product is relatively new. It's a 1 year old, meaning in terms of general availability. It's available in 2 regions. So it's available in Frankfurt and in North Virginia. And it's expanding. So it's expanding both horizontally and vertically. So both feature depth, but also kind of region of availability. This is very exciting for all of us. You will hear a lot of new things around the service in the upcoming months. So yeah, thanks a lot for having this opportunity with you today, Alina. Really appreciate.
Yeah, thank you very much. And I think now, as a bit of a closing, I would like to ask you, if you want to, if developers want to get started, like where is the material to get started? I put already a couple of links, but I believe that you mentioned to me at one point that there are ways to get started with cheaper hardware that developers can just get and connect to their cars. Maybe let us know a bit about that.
Right. So I think you posted the link already. So our developer guide has a step-by-step onboarding guide that with a couple of click of buttons using CloudFormation templates, you could, if you have an AWS account, you could already start building your first demo using purely AWS without any hardware. So the link to that is, I think it's posted in the link there. It's our quick start demo. I will post it again here in the chat. So I'm not sure if I can post comments here or you can. Alina?
Yeah, I can, but you can paste it to me in private chat, and then I can post it in the chat for everyone if it's a different link.
No, it's the same. It's the same. So they will find so they will find the quick demo script. So that's, as I said, the prerequisite there is only an AWS account. If they have an AWS account, they go ahead, they will follow the script, click button, CloudFormation template, create an EC2 machine. It will run the agent for them. It will create a campaign on their behalf. It will show them the full capability. The other thing is that if you are moving from the cloud towards real devices, we have, as I said, certified devices that are also, there is a tutorial for every device. We have been working with the iWave system. iWave is a manufacturer of TCUs. We have a tutorial there. If you don't want the iWave, you want to go with a Raspberry Pi, there is also a tutorial for it. There is also another guide for running it on a small dongle, right? 10 euros on every, easily you can find it on Amazon, plug it to your car through the OBD connector. And we have even an Android phone application that you could try on your Android phone, just install. It's also available as part of our GitHub repo. So all of these developer tools are already available to experience the service at almost no cost. I think that's what I really look forward to get your feedback here. And yeah.
Yeah, so I'm just pasting the links. I think I found the link to the Android application as well, and also the link to the cheap device on Amazon that you can actually get. This is just
Correct.
an example. Of course, you can find your own connectors as well. So yeah. Yeah, all right. Thank you very much, Anis, for this. This has been a really, really interesting session. So I've learned a lot, and I'm sure that everybody watching has also learned a lot. Again, for you all, if you have any questions for Anis, paste them in the comment section. If you like the video, give us some feedback. If you like the stream, give us some feedback. If you want to see something different, let us know, and we will be happy to accommodate. So yeah, this has been all for today. I wish you all a really pleasant afternoon if you are in Europe, or morning if you are in the US. And yeah, see you in our next episode. Bye.
Thank you very much. Bye-bye.
Thank you. Bye.